Now let us see some results based on multiplication of two different series, which are the binomial expansions, and one of these is written in ascending order whereas another is written in descending order. So here is the first result, which is MCR plus MCR minus 1 into NC1 plus MCR minus 2 into NC2 plus so on up to NCR is equal to M plus N CR, where R is less than M as well as R is less than N, and M, N and R are the natural numbers or positive integers. Now here let's start off with LHS and let us try to see some pattern or connection between how these products are arranged. Now if you observe, except the first term, all the terms ahead are having two binomial coefficients in that. So looking at the pattern, we will clearly see that the first term must have NC0 as the second factor, which is not written because NC0 is 1. So we still write it for the sake of checking the pattern, and let us write the remaining terms also. Now similar to first term, the last term is also having one missing term, that is MC0, and the next term is NCR. Alright. So now here if you observe, all the terms that have M on the top, we will see that the lower terms, or rather the lower numbers, are decreasing from R to R minus 1 to R minus 2 and so on up to 0. Similarly, if we see the second part, that is second factor, it is having N on the top, and the lower number now increases from 0, 1, 2 up to finally R. So what does this mean is, if we look at the two different series, that is first series is nothing but say 1 plus x whole raised to m. So you will see that it will have MC0 plus MC1 into x plus MC2 into x square and so on up to finally we will have MC say m x raised to m, and somewhere we will have a general term, that is MCR x raised to r. Alright, so this is the first term, that the first series we have to consider. Now let's consider another series in which instead of m we have n as the index. So here what happens is, let us rewrite the terms once again. Here we will have, instead of m we will have n, nc0 plus nc1 times x plus nc2 times x square plus so on. Somewhere we will have a general term ncr to x raised to r plus so on to finally ncn x raised to n. Now let's try to see what does each product means. Now if you check MCR into NC0, see here the product is MCR, which is here, and NC0 here. When you take the product of these two terms, we will still have x raised to r in that product. Alright. Now next, let us consider the next product, that is MCR minus 1 into NC1. So NC1 term is here and MCR minus 1 will be the term which will come just before the term which we saw. So it will definitely have x raised to r minus 1 as the term in that, x raised to r minus 1. Now if you take the product of these two highlighted green terms, x multiplied by x raised to r minus 1 is going to give us x raised to r once again. So you see that in each of this product we are going to have x raised to r as the variable part. Alright. So therefore we can conclude that the required product is always the coefficient of x raised to r term when we multiply the two binomial expansions of 1 plus x raised to m and 1 plus x raised to n. So with that, let us rewrite the required series as like this. So this is equal to LHS is nothing but coefficient of x raised to r in the product of 1 plus x whole raised to m into 1 plus x whole raised to n. Right? So that in turn is equal to coefficient of x raised to r in, when the base is same, we can definitely add the indices and say that this is equal to 1 plus x whole raised to m plus n. Now the coefficient of x raised to r in 1 plus x raised to m plus n is nothing but, as we know from the general term, it is m plus n c r. So therefore this is nothing but the RHS. So in this way we have proven the required result. Right. Now let's move ahead and see one deduction based on this particular general result. Now here we have NC0 the whole square plus NC1 the whole square and so on up to NCn the whole square is equal to 2nCn. So the left hand side is nothing but sum of squares of all the binomial coefficients. Now let's consider LHS first. Now each square we can definitely write as the product of the same terms, that is NC0 square is nothing but NC0 into NC0 plus NC1 into NC1 and so on up to NCn into NCn. Now if we compare this with the previous result, there one of the series was increasing and another series was decreasing, but here we see that both of the terms which are in the each of the product are increasing. So that means somehow we must convert one series from increasing to decreasing. So we can easily do that using the property. Now this NC0 I can write as NCn because of the property that NCr is always equal to NCn minus r, and we know that the binomial coefficients are symmetrically equal from both ends. Similarly, the next term NC1 as it is, and NC1 now I can write as NCn minus 1 and so on. Finally till we have NCn, and the second NCn I can write as NC0. Right? So now this further is equal to, as we have seen in the previous result, this has to be equal to coefficient of x raised to n, because now we are talking about all the terms from NC0 to NCn in the product of 1 plus x raised to n as well as 1 plus x raised to n, because in both of the cases we have top numbers as equal to n. So this is nothing but equal to coefficient of x raised to n in, here we have 1 plus x the whole square and that raised to n, so that gives us 1 plus x raised to 2n, and coefficient of x raised to n in 1 plus x raised to 2n is nothing but simply 2nCn, which is nothing but the RHS. So this again proves the required result. Let's see one more result based on this. Now here if you observe, it's again having the squares of binomial coefficients, but now the signs are alternately plus and minus. So the result also depends on the nature of n, that is if n is odd then this particular expression is equal to 0, whereas if n is even then the answer is minus 1 raised to n by 2 into n by 2. Now let us see how we can prove this. For this we begin with LHS and once again write NC0 into NC0 minus NC1 into NC1 plus NC2 and so on up to finally we have minus 1 raised to n NCN. Now using the property once again, NC0 we will write as NCN, then NC1 we will write as NCN minus 1 and so on up to lastly we will write minus 1 raised to n into NCN, and the second NCN we will write as NC0. Right. Now here we can see that here also both of the series are having n as the index, but since the alternate terms are positive and negative, that means one of the series can be considered as having all the positive terms, whereas second series is having the alternately positive and negative terms. So therefore we can reason out that this particular expression is same as the coefficient of x raised to n in the product of, see the first series in which all the terms are positive we will consider as 1 plus x raised to n, and now the second series in which we want the alternately positive and negative terms has to be 1 minus x whole raised to n, because when the second term is negative we will get alternately plus and minus terms. So this in turn equals coefficient of x raised to n in, we can club 1 plus x and 1 minus x into 1 minus x square whole raised to n. So now here we have to find out the coefficient of x raised to n in 1 minus x square whole raised to n. Now if we consider a general term in this particular expansion, say TR, now this will be equal to NCR into minus x square whole raised to R. Because here we have to consider general term as R plus 1 if we are writing R in the right hand side. Alright, so this is how the general term appears. So just rewriting that, we have NCR minus 1 raised to R minus 1 raised to R into x raised to 2R. So if we write that as x raised to 2R, so that means if we want to find the coefficient of x raised to n, and here we get coefficient or rather the index of x as 2R, which will always be an even number. So that means we will find the coefficient of x raised to n only if 2R is an even number. That means n has to be an even, okay, because R is n by 2. So therefore on the other hand, if say n is odd, then it means that R is not an integer, because R will be equal to n by 2 as we can see here. So R will be equal to n by 2, which will not be an integer if n is odd. So that means now here we have two cases, or rather the two possibilities. That is, first, if n is odd, then we will not find any term in x raised to n. Okay, so therefore here we get the first result, that is the required sum will be equal to 0. Whereas if n is even, okay, then we have the general term as T R plus 1, which is nothing but n by 2 plus 1 is equal to n c n by 2. That is, what do we do is, in this particular term we simply put r as n by 2. That is equal to n c n by 2 into minus 1 raised to n by 2 and multiplied with x raised to 2r. But now what we are going to do is, now as we have done in previous cases, we are going to substitute x is equal to 1 so that we don't have any variable term and we can easily evaluate the required expression. So therefore finally we get, if n is odd then the required expression is equal to 0, and whereas when n is even then the required expression reduces to nc n by 2 into minus 1 raised to n by 2, which is the other required case.